Good afternoon.
Good afternoon, sir.
How are you folks doing? Did you hear the good news? You did, huh? Already? My God, I'm the only one who has heard it very late. By the way, this is the sixth time that we have been.
Congratulations, sir.
Congratulations to you people. You made it happen. 12 p.m. announcement, is it? Oh, okay. Not bad. Within an hour, I could get the information.
Sir, I also heard some this. I do not remember the name of the organization. They put a rank of universities around the world. They said that IIT, all our old IITs has like refrained from ranking. I heard. Is this correct, sir?
I don't know what the decision has been. Perhaps MHRD would have asked IITs not to get involved. See, there's a lot of things that go on. Anyway, forget about all those. Just enjoy the moment. That's all. All this ranking and all those are only something that you don't have to be too bothered about it.
No, I don't bother about that, sir. But when the institute's rank goes high, country's reputation also goes high. That's that's the only thing.
But it depends on what criteria that you use, no? If it is number one ranking because, right? There's a lot that goes on at the background. So let's not talk about it.
Complex things, sir.
But the point is, if they have refrained from it, there is a valid reason for doing that. Okay. And these are companies that mint money because of this. So in a way, anyway, forget about that. Congratulations anyway. So folks, what happened today? A lot of you are only a few have joined today. Did you have a class before this? No. It was lunchtime. Okay. Any questions? Yeah, new Kaveri also. When I was dean, it started. By the way, my alumni hostel also will be getting a phase shift. Godavari hostel.
I am also gonna be an alumni of Godavari, sir.
Okay, fantastic. So it's looking nice. Currently, I don't know who is staying. I think it's currently empty. It used to be first year undergraduate hostel for a few years, but no, the 2021 batch may move to the new hostel, Mandakini. Okay, that will also be ready in a month or so. So, and it's a large capacity hostel, about 1,250 can be accommodated, more than that. So, lot of good news, huh? Okay. Kaveri won't be for you. You will all go into different hostels now. Okay. So Kaveri will be a postgraduate hostel, a research scholars hostel. Kaveri, Krishna usually are institute. We don't know. It may open soon. The way it goes, we're not seeing third wave, so just touch wood, hope for it. Make sure that you don't you wear mask and have all those observations related to COVID. Tell people so that there is no third wave. January may come back. All right. So let's go back to our class today. Any questions on whatever we have discussed so far? Okay, how many of you have this? I didn't buy it for NIR of 1, but how many of you have this? I'm talking about this. None of you? None of you have it? Can't get it. You must be here at the mall. Is it? Okay. Okay. No, it got delayed. I had to complete the part on stresses before taking this up. I should have asked you to, I should have reminded you, but somehow it just slipped my mind completely. And I just ran to get from the store nearby. Anyway, if you have it, this is what you do. When you press it by the side like this, you can see it slipping, right? Rather than separating. Separating seems to be a little bit more involved compared to just pressing it. That's the beauty of wafers, right? I love wafers because of that. I can just apply the slip. Look at this. It's an old stock, so it already sheared. Why do we call it sheared? Because it is actually going through a motion that is along the plane, which is a weak plane, right? We discussed this a little bit yesterday. I'll start off from there, okay? There are many examples that one can take up. Supposing I have a point P, okay, on a large body, okay, and I'm observing this particular point P, and let's say I have stresses that I could find, okay. And let's say that is nothing but this wafer, okay. It seems to have a slip plane like this, okay, or it seems to have a plane along which it's easy to slide it rather than removing it, right? Now the question is, how do I find out the strength of this material, right? Remember, strength is associated with failure, right? Pass is associated with fail, right? So strength is associated with failure. So I will ask and ask, when will this material fail, right? What do I mean by failure? Here, failure I would attribute to starting to slide, which means that there is a particular shear stress that I have to overcome before it starts to slide. Okay, it could be because of the cohesion that is there with the wafer sheets that we have this kind of a thing. So in a way, I have something like this. I've just I'm showing only one of this, but it could be many like this, as I have shown in the board. So when for example, if I apply compression here, it seems to get compressed. In total, it has compressed, but compression has happened because there is sliding internally. Okay, and this sliding is such that it doesn't come back to its original shape. It remains like this, which means if I have a function of a particular, let's say an object, let's say, what should I, okay. So let's say this is the object, right? And some force is applied and it got twisted like this. If it remains twisted like this, the function of this box
will get debilitated, which will come down, right? So one way to describe the strength of the material is to ask when will it start to show permanent deformations. Okay, very crude in my way of putting it, but perhaps this will help in terms of understanding the strength. Okay, in this case, what will affect it is when sliding occurs at any of these planes that we are talking about. There's only one directional plane that I've shown over here. So which means that if it has to fail, it should slip like this. Okay, and this slipping occurs because there is a shear stress that is affecting that kind of motion, right? So if I'm able to find out this shear stress, let's say I'm going to call this as tau theta. If I'm able to find out this tau theta, and if I ask this question, has tau theta reached tau? I'm going to call this as critical. Okay. If the answer is yes, then the material has failed. If the answer is yes, then I would say, oh, okay, now I know what the strength of the material is. Okay. If the answer is no, that means the material can withstand that particular stress. Okay. So strength is associated with going to that limit when this shear stress that I found out from sigma x, sigma y, tau xy. So this is related to that. If this goes to a critical value, then that particular state of stress I'll call as strength of the material. Okay. In a way, I can use this as the strength of the material. In an assignment problem, you did one of the assignments where it said yielding, right? This is primarily what is yielding. Remember, even though it is sliding, it is still, the object is still intact. The object is still intact, or the material is still intact. Okay. So what has happened is it has yielded to the stress that has happened. Okay. And therefore it is called yielding. Okay. So yielding is one way of attributing the strength of the material. Is this clear? Very simple. And this understanding will help us proceed further. Any questions? But it will be in regard to shear stress. Different we see for longitudinal. Okay, I'll come to that. Fantastic question. If this is clear, I'll move on. That is, if I know that this is the plane along which it can slide easily, then I'll find out that shear stress and find out how close it is to tau critical, so that I get an idea of whether the stress state is something that it will withstand or not. Okay. Now this stress state can be anything. It can be just like this. It can be like this. It can be like this. It can be like this. There are many possibilities that you could have. It can also be like this. Doesn't matter. If I know this stress state and I have the sigma x, sigma y, tau xy, then I can go ahead, find out the strength of the material. Okay. So is it longitudinal? Supposing I do an experiment. Let's see. Okay. So I do an experiment. I do an experiment which is a longitudinal load that I apply. And at a particular load level, it starts to now slide. Okay. And I noticed that through drawing the deflection versus. So if I remove the load, if it comes back, then it is elastic, no problem. Okay, so I can again apply the load, it will again take it, etc., etc. But the moment it has started to slip like this and does not come back, okay, that means it has reached that state where its purpose or function is debilitated, is reduced. Is this clear to you? So if it is longitudinal and if it is some force that I have to apply over here, or this force leads to stress in this direction, right? This stress in turn will produce the shear along this weak plane, and I can find out that shear stress and find out whether it has reached the is the stress state something that the material can bear or not. So far so good, simple. Is this clear to you? In a way, I can put it in a little different fashion. There are many such possibilities. For example, if you take a pack of cards, a pack of sheets, or all this, and when you press slightly at an angle, it will tend to more slip rather than get pressed permanently. Okay. The reason is the strength in the direction that is perpendicular to the weak plane is higher compared to along the weak plane. Okay, and therefore this scenario that happens. For example, this one that I often use it is nothing but magnetic beads, magnetic balls that are clinging together. Okay, so when I press this, what happens is one ball slides over the other, and remember it is not separated into two like this. Okay, when I press this or pull it, it remains a permanent deformation, but it is intact. Okay, unlike a separation that you see in some materials. Okay, in that sense, as I pull it over and over and over and over and over, if it is elongating rather than breaking, we call that material as ductile material. Now let's associate ductile material to that which has to do with sliding because of shear. The second point that I'm talking about. Should I repeat this? So we started with saying, okay, there is a weak plane. The weak plane has is such that it can slide easily compared to separating. Okay, and then we found that through a simple understanding that the material is still intact. It has not separated into two pieces and all this. It is still a continuum, right? And I can elongate more and more and more. Something that some material that can be elongated more and more and more is a material that we call as ductile, correct? Right? Right. So I can associate ductile materials with the weak planes that exist in the material that give way. So far, so good. All right. Now, if you take metals, for example, so shall I erase this? If I take metal, so I'm just going to draw something that's a cartoon of the small portion of metal. You will have grains in them. Okay. If you see through the microscope, you will be able to see such grains, and each grain is a crystal. Each grain is a crystal. Like this, okay? Each grain is a crystal, and if I look at this crystal, the crystal will look like a lattice with a lot of weak planes. When I say a weak plane, I may have a strong plane, a dense plane, and I may have I may have another dense plane going along the same along the same plane, such that it is difficult to move them in this direction compared to this direction. Okay, they can easily slip because dense plane wants to be intact. Okay, and there are a lot of such weak planes that are possible in a crystal. For example, if you have a face-centered crystal, you can have as many as about 12 weak planes. On the other hand, if you go for body-centered BCC, you have double the number, 24 of them. Okay. For example, aluminum is face-centered crystal, steel is body-centered crystal, and so on. Titanium is face-centered crystal, which means that it has so many weak planes. As the number of weak planes increase, what happens? It becomes more and more ductile. Okay, so these are some materials that are more and more ductile. In common, most metals have a crystalline structure such that the number of weak planes is very high. Okay, and therefore, in general, I'm not going to go in particular. In general, metals are ductile in nature. Okay, all right. Now we looked at only one plane. Okay, we looked at only one plane, but if you look at this, there is one plane like this, one plane like this, one plane like this, one plane like this, one plane like this. In other words, you take any orientation, there will be at least one crystal which has a weak plane that is along that orientation. Okay, and there is more likelihood that if the stress matches the tau critical, it will start to fail. Okay. Now, among these, let's say I have one plane here, two plane, three plane, 4, 5, 6, and so on. Which plane will first slide? That's important to me because the moment one of the slides, it means it has reached its threshold of strength, right? So we asked that question: which plane will first slide? Okay, which plane will first slide? I can find out the shear for this. So let's say this is tau 1, and this is tau 2, tau 3, tau 4, tau 5, and so on. Which plane? This is a question I'm asking you. Which plane among all this will first slide? Assume that all the planes have the same tau critical. So all planes have tau critical as a property of it, tau critical as threshold for sliding. Which one would first slide? Which one would first slide among tau 1 to tau 2, tau 3, tau 4, tau 5, and so on? Plane which has the shortest length. No. See, remember, this is just a small piece that I have taken. This is a part of a large material. This is a material point I've chosen. Okay, microstructurally, it shows something like this, and therefore there is no shortest length that I can attribute to. What would it be? Which one among all this tau 1, tau 2, tau 3, and so on? How will I identify this orientation where it will first? This is the first sliding. How will I identify this? Anybody? Which has the highest what? sigma. I don't have sigma at all here. Only I have tau only. Karthik. All planes may not slip. That's the question I'm asking. Which plane would slip first? Supposing I know the stress at this point. I know the stress at this point P that I have chosen. Which has the highest what? Sigma or it's slipping. What is responsible for slipping? Highest what? Shear. Exactly. Shear stress, not force. Shear stress. So if I find out tau max for a stress state, let's say this, remember this is a tensor, right? Or in other words, it will be sigma x, sigma y, tau xy, like this. It could also be three-dimensional. Okay. If I find out the tau max for the stress state sigma, then I can say when tau max goes to tau critical, then the first sliding would start to occur. So if this is the orientation of tau max occurrence, then it's possible for me to find out not only orientation, but also when the material will fail or the strength of the material associated with that. Okay. And this tau critical is the one that governs it. But remember here, it is tau max that I need to find out. Okay. Is this clear? Is this any questions? Very simple idea. Okay. And this was proposed by Tresca. He did fantastic set of experiments. Okay. Till then, people did not know. I think it was back in the 19th century. He said, okay, if I know the stress state, and if I can find out tau max, right, it is possible for me to find out the strength of the material. Okay. Now, how will I find out this tau critical? That's not very difficult. I'll take the material, pull it, find out when the yielding starts to occur. Okay. And let's say that stress is, so shall I erase this? How do I now find out the tau critical? That's the next question. Okay. How shall I find out? That's very simple. All I have to do is I'll take the specimen, apply, let's say sigma, okay, and I find out due to this tau max. Remember, I can take a small element over here. The small element will have sigma like this, okay, and therefore the stress state for this is sigma 0, 0, 0, 0, 0, 0, 0, 0. Right? Is it not? And I can find from this tau max. Okay. You can draw the Mohr circle and find out what would be the tau max. Okay. So it's possible for you to find out tau max. Okay. Tau max will have 0 here and one of them making be tau max. Okay. Once I find out tau max, I know when it has started to yield. Okay. Let me call that as the stress at which yielding has occurred. Now I will associate this with tau max. So tau max associated with sigma y will give me the tau critical. Therefore, it's very easy. I'll do a tension test and find out how it is. Now, remember, we did this exercise earlier and we found that tau max occurs. Can you draw the Mohr circle for this? The answer is yes. How would the Mohr circle look like? Sigma 1 is equal to sigma sigma 2 is equal to 0, right? So this is sigma tau here, right? So this is one point, the other is sigma over here. So let me call this as sigma y, and I can draw the Mohr circle, right? This is the radius, which is nothing but sigma 1 by 2. And this is also radius, and this is also maximum tau, right? And therefore I have tau max is equal to sigma y by 2. So I did an experiment now, found out sigma y by 2. Now you give me any stress state, I'll tell you when the material will fail. So simple. Okay. And that's what Tresca came up with. Beautiful, no? Very simple idea, but very powerful idea. All right. Any questions? So I can draw a Mohr circle and show you. As you can see, the axis of Mohr circle is sigma and tau, right? The normal stress and the shear stress acting on that particular plane, whatever plane that we are choosing, correct? So let's say it is like this. It is like this. Now, what did I say failure would be? When tau maximum goes to tau critical, right? Or in other words, I can write this as tau minus tau critical equals 0 is the equation. What is that? So if this is tau critical, then this is the curve that I'm looking at. So if I draw the Mohr circle, if the Mohr circle is not touching it, then it means that this is a safe state of stress. Okay. So far, so good. Are you able to understand? Okay. How did I get this? This is related to the material that I tested and found out what would be the tau critical. Now I can draw this. Okay, this basically tells me for a ductile material, I'll be able to do this and examine whether the stress state is safe or not. So if I have something like this, let's say there is one more stress state that I draw, and it happens to be something like this. I know it has already exceeded, which means that this stress state is unsafe. Very simple. And what is this applicable for? The materials which have weak planes for sliding. Okay. When I say weak plane here, it is weak in with respect to sliding. Okay. What do I know already? That is also an information. Sliding is preferred compared to separation. Okay. So if I take two planes, if I take two planes and I pull them apart, let's say it takes some stress for me to pull that. And let's say I have shear that I apply without any stress on it, right? And this shear is very much less than sigma that I need to apply in order to slide it. And therefore, this dominates the failure of the material. So far, so good. So you may ask the question, are there materials where the normal stress dominates compared to the shear stress? The answer is yes. Okay. So there are materials where the normal stress dominates compared to shear stress. So we'll look at that also. Okay. Any questions? Any other questions you may have here? Any other questions? If you don't have, let me move on to the next one. The simplest example that you can have is a piece of chalk. which one should I break? Is a piece of chalk, right? So if I pull it or cut it with a pair of scissors, when I cut it with a pair of scissors, okay, this action has to do with taking this sheet. You did this in your one of the assignments. It has to do with applying something like this. And if I take this region and explode it, it has one force coming in like this, and the other force coming in by a very small delta away. Okay. And within this region, if you look at it, it is predominantly seeing shear stress, right? And therefore, a pair of scissors is easy to use when I need to cut or fail a material. Okay, it could be a pair of scissors, it could be a sheet of paper, etc., etc., etc. You've already seen that. Okay. On the other hand, if you notice, I also did one more experiment. Let me see if I have that over here. Where is it hiding? Oh, unable to find. Here. On the other hand, I did this experiment. Now, when I tried doing this, it was not cutting properly. Okay. So perhaps this material has a property which is different from being failing because of shear, because of weak plane sliding. Okay. Perhaps the weak plane is such that it is just separating easily compared to sliding. Okay. So we'll look at that also. Okay. One of the other examples that you know is a piece of chalk. When I pull it, it breaks very nicely with a plane that is perpendicular to the pulling action. Okay. All right. So again, I'm going to draw the same thing. A plane, point P on a material. So this is a material point that I've taken. And let's say I have a plane which is a weak plane, but now the weak plane is such that it is easy to separate it rather than slide it. Okay. So how do I now find out the failure of this material? Again, the same thing I can do. What is it? I'll find out the normal stress in this direction, right? And equate that normal stress to a critical value. Okay. I can equate that normal stress to critical value to know when this will occur. Okay. For example, if it has sigma x, tau xy, sigma y, then what I'll do is I'll find out the stresses along this plane, okay, which is in this direction. And I have a normal stress over here, right? And let's say this is sigma x prime y prime. I'll not bother about other stresses, but I'll find out whether this has exceeded sigma critical. So I'm going to call it a sigma failure.
Not able to hear you, sir.
Yeah, the connection just went off for a second. I think I have finished this, is it not? When normal stress goes to a limit. sigma x prime y prime goes to sigma f, then the failure occurs. Now, I can understand again through a more circle understanding. I can have sigma over here, tau over here, and let's say I have the stress state that I'm drawing over here. This entire circle is a stress state. Okay, if you understand this, marvelous. Becomes easy for you. Now, if I ask you, okay, this is the orientation, so I have orientation that I have. What I'll do is I'll find out what this is and equate that to sigma f, right? Okay. Now, I can do a very similar thing over here, like what we did for different planes. I'll ask that question, okay, there is no one single plane. Any orientation you take, there is a weakness in terms of separation. Okay. In which case, what should I do? Instead of sigma x prime y prime, I should ask, when is sigma max going to sigma critical or sigma f? Okay. Or in other words, sigma minus sigma f is equal to 0 is the line that I draw in this. So let's say that is this line. Okay, this is what is this? This is sigma minus sigma f is equal to 0. That's the equation of the line. Okay, is this stress state safe? The answer is yes. All right. Remember, I have drawn it in the tension. Okay, we'll come to the compression later, but in tension, when it reaches this particular value, it will now no more stand stress, gone. So if I have a Mohr circle that is like this of a stress state, this means that this is not safe, whereas this is safe. Simple but yet powerful. Okay. So we looked at two scenarios. One in which the weakness is along the plane, which is sliding. The other is weakness is in separation, right? These two are the phenomena that occur. Okay. This is due to ranking. Okay. They also call this as maximum normal stress theory. Okay. Or principal stress theory. Why principal stress? I know if I move this line, the tangent called maximum and principal stress theory. Okay. So far, so good. Is this clear? Any questions? Let's see if there is an intelligent question that is asked. You're all very intelligent. So I know you'll ask one typical question that I'm expecting. Oh, one typical question that you may ask. Go ahead. Is there a question that you have? We looked at two scenarios. One that is weak in shear, the other which is weak in normal stress. Would you have a question? No question? Perhaps many of you are hungry. You should have brought this wafer. No, yes. Is there a scenario? Fantastic. Yeah. Anirudh, thanks a lot. Yes, that's the question I was expecting. Well, is there a scenario? Is there a material that is neither this nor that, or both? That's what Anirudh is asking. It has weakness, but not necessarily only in the normal stress condition or weakness along shear. The answer is yes. One of the simplest understanding that we have is this. Shall I erase this? So the question is like this. I'm going to translate what Anirudh asked as a question. Sigma here, tau here. We had one failure which was like this, right? There was another failure that was like this. Okay, this is sigma minus sigma f is equal to 0. And this is tau minus tau critical is equal to 0. Okay, two scenarios we saw. The other possibility is what? Well, I know one scenario where if I have a block and there is a normal force, I'm going to deliberately use stresses over here. Okay, sigma is the normal stress and there is a shear stress, okay, tau, right? I can ask the question, if this is a frictional surface, is there a dependence between these two? That is, if I ask you, at what tau will it start to slide? This is a beautiful question, right? And the answer is very simple for you. What is your answer? What is your answer? Well, sir, it depends on the sigma. If the sigma is higher, then I would get a higher value that I have to overcome as far as shear stress is concerned before sliding can happen. You're all very silent today. See, there is no sound bite, there is no video bite. So it's very tough for me. I mean, you don't know what I'm going through. That's why at least on the chat box, I should see something. Okay. Even if you say hello, it's fine with me. All right. Is this clear? Is this clear? This is the most important thing that we understand. Here, there is a relationship between them. Okay, which is what? Well, this is tension, this is compression. Let me erase this. This is a negative direction, which means compression here, tension here. So at particular point over here, you don't need any shear for it to shear. Okay, just like water, any fluid. Okay, else it will be something like this. All right. So this is tau is equal to, let's say, m sigma plus c. Okay. I'm going to deliberately introduce minus over here because I know the compression matters over here. Okay. Is this clear? Right. And this we can attribute to frictional. What kind of friction? Dry frictional. Okay. So this is a dry frictional line. One may ask, sir, is this the only thing, Shiva? Is there anything else that is possible? Of course, yes, it can be something else also. It can be something like this also. Okay. It can be something like this also. It doesn't matter. It all depends on the material that I have chosen. Okay. But most materials fall under either this, which is most metals, these most brittle materials, and these which are frictional materials. One of the simplest material that you know of, which is a frictional material, is any answer? Frictional material means there is a relationship that is there. Any answer? Frictional material, which means that if there is normal force, it changes the value at which the failure occurs. So this tau minus here, I have not put anything over here. So I need to now add saying that tau C is equal to, where tau C is the critical value. Remember earlier we had only tau here. Now we are putting it like this. Any questions? Weak in bending. Yeah. Don't bother about bending and all this. Bending is an action We are not looking at action. We are looking at only a stress at a point. If I'm given a point, then ask the question, okay, what are the stresses in it? Doesn't matter whether it is pulling or bending or twisting or anything. Okay, we'll come to each one of those later. Okay, what kind of stresses are produced? Clear? Yeah. I'll stop here. The way that you can understand this is if you are in this region, you can have a Mohr circle like this, which is to do with the testing that you have done and failure has occurred over here. It could be another stress state where the failure has occurred over here. So if you join all these Mohr circles with the envelope of this, you will get this relationship. Okay. So at least two Mohr circles you would need in order to draw this. Whereas this will need only one, which means that I should do two tests for a frictional material, whereas a material like this or like this will need only one test. So let's say just a tension test will do. Okay. This looks simple, but very, very important for us for our understanding. Perhaps Titanic would have been saved if we had this understanding. Okay. Good, folks. Enjoy the festive weekend. Binding of books, files act like friction. Yeah. So now you can understand easily. Wherever there is a frictional part coming. So there are two things. One is cohesion. The other is frictional. Okay. If I use an adhesive, cohesion is the primary action, right? The other is frictional or so cohesion and friction are the two parts that I look at in order to model the failure of a material and therefore strength of the material. Okay, we'll go through a lot more of this, but pertaining to stress, I thought I would give you an early bird picture of how we understand failure from just understanding transformation of stresses. Okay. Okay, folks.